Hello everyone, my name is Massimo Banzi and I'm the co-founder of Arduino. And in this presentation, I'm going to talk to you a little bit about the process I went through to develop a couple of devices that could be used as a predictive maintenance tool. I call it a journey because it's an experience I went through to experiment what it meant to build something like this from the point of view of a user with not a lot of experience in machine learning. So, well, first of all, Arduino, our mission is to enable anyone to innovate by making complex technology simple to use. Back in the days, this meant microcontrollers, then it became connected devices, and now there's a lot of work done to try to simplify also the machine learning aspects of embedded computing with a preference to what they call tiny machine learning. But the idea is take these complex technologies and to present them in a different way so that they become much more understandable by a wider audience. So Arduino is super popular. So just this is just numbers from the different properties. It's just to show that it's now a very big community, very large amount of people that work with Arduino at different levels, from education, from personal sort of projects to research, prototyping, and also more professional projects that I will discuss in a few seconds. Some of the numbers are very interesting. Like, for example, the 4,000 libraries from Arduino. These are building blocks that make Arduino code essentially very low code. You can build complex application with few lines of code because you have all these pre-made blocks that you can actually use, and they're all open source, so you can customize them. You can even fix problem if you want to change a little bit the way they function. But what about Arduino Pro? So in the last 3 years, I guess, we put a lot of accent on this idea of Arduino Pro because Arduino boards have been used in professional setting for a long time. Every major corporation has used Arduino to prototype, design products. There are Arduino derived boards in a lot of products. But for us, pro doesn't mean trying to build something for the world of professional embedded engineers, but it's to look at the people who are professional in their businesses. A lot of times they are small and medium enterprises, but sometimes we also work with very large companies. And the idea is, how do you enable this kind of um, companies or projects to actually implement Arduino to build professional project in a professional company setting. So we've been working on this a little bit, and now I'll show you a little bit of the tools that we developed for that kind of audience. So for all the hardware that we developed for this new Pro initiative, the first one is the Portenta H7, which has been around for about 3 years now. So it's got a very small form factor, but it's packed with features. So the main processor is a STM32H747, which is a dual core uh, ARM Cortex-M7 coupled with an ARM Cortex-M4 processor. But then on the same board, you can have up to 64 megabyte of RAM, 128 megabyte of flash memory. There's a crypto chip for secure connectivity. There's Wi-Fi, Bluetooth, Ethernet, CAN, USB-C with display port out, so you can have video out. So I think it's a small module that packs a lot of computing power and has this high density connector that allows you to snap it to modules like the Portenta Vision Shield. It carries two types of very low power cameras from Himax and dual microphones. So you can do beamforming as well. And it supports Ethernet, LoRa connectivity, and it's got an SD card. So you can snap this on the back of a Portenta, and you basically created a connected low power camera that can run on a battery and can do low power computer vision tasks. So that's kind of the idea. Another piece of hardware that's quite relevant in this world is this machine control. This is a piece of hardware you can snap a Portenta inside, and it turns into an industrial controller. So all these IOs that are breaking out on these screw terminals, they are basically going through some heavy-duty industrial IO type of interfaces so that the microcontroller can interact with equipment where there might be also some dangerous voltages or different kinds of interference, but it also has all the different protocols you need in an industrial setting, RS485, Ethernet, CAN. So there's a lot of different protocols available. So somebody that knows how to use Arduino, which now means millions of people, can actually develop an industrial application with tools that have been built to industrial standards. So both all the Portenta Pro family, all the different tools are built, designed and built for industrial temperature, industrial kind of strength, so that you can actually use them in real life applications. Just very quickly, we also have this IDE 2.0, which is coming out of beta. This is much more professional. It's got a debugger. It's got a lot of different things. It's derived from the same framework as Microsoft Visual Studio Code. So it's a much more sort of professional way to develop with Arduino code. And finally, there is OpenMV for Arduino, which is essentially a MicroPython-based platform that allows you to do computer vision and also machine learning on microcontroller platform, and it supports a few Arduino platforms. So it supports the Portenta, and it supports also two ARM Cortex-M 0 and M4 based Arduino products. So this makes it very, very easy, and I'll show you an example later on in the presentation, so I'm not spending too much time on this now. So let's look at condition monitoring. And so obviously working more and more with companies, we see a lot of situations where companies have older equipment that it's sometimes just even just electromechanical that they want to integrate into an Industry 4.0 type setting. So the idea is, how do you build tools that easily integrate this into these sort of network systems? And how do you monitor certain conditions without having to have any heavy interference with the machine? So one of the things that that I looked at in an idea to try to make things simple for people to understand, one is vibration monitoring. Machines produce different vibration while they work. And sometimes, from these patterns, you can understand if they're operating correctly or not. There's a lot of stories when you talk to people in factories of, older people working in the factory. They can just put a hand on a piece of equipment and understand if it's working or not working properly. The other use case I looked at is there's a lot of these electromechanical indicators on machines. And essentially, if you want to take the data and bring it to some kind of a cloud platform, either somebody goes and sort of manually read it and sort of types it somewhere, or we can build something that looks at these kind of dials and brings the data to a cloud. Let's start with vibration monitoring. So the objective was to build a device that could be just bolted on a piece of equipment, and then it could detect, could be trained on different patterns, and then detect when it was kind of deviating from this pattern. And I wanted to manage this from the Arduino Cloud, and I wanted to do as much as possible inside the device. So I'm using this lightweight framework called IVES, which I will talk to you in a second. So this is the setup. It's a Portenta with this IMU shield on top. The IMU shield contains a Bosch SensorTech BNO055, which is a very sophisticated 9-axis sensor. It's way more than it's needed for this application, but it's got nicely snaps on top of the Portenta, so I use this. And I simulated a piece of machinery by having this box with the vibrating motor inside, powered by an Arduino. When I press the button, I can generate 3 different types of vibration patterns that I try to pick up with the accelerometer. And then here you can see some snapshot of the waveforms that were coming out of when I made my experiment. So I started to say, okay, let's figure out how do I extract features that I can then use with a simple neural network to detect if there were some variations. So first of all, I started to apply the fast Fourier transformation. So I applied this FFT to some of the signals, and I started to understand what are the different frequency components in the different signals. So I thought that could be a very interesting way to analyze the signal. I also tried to visualize it in spectrograms to try to understand if this could be used as a way to understand these kind of patterns. So in the end, I went for a simple setup where I was capturing the data from the IDMU, apply a number of filters to filter out different kind of noises and calibrating the different axes. And then I kind of figured out ways how to combine a little bit the different signals and then applying a window algorithm so that I could extract a window of data that I could pass to the FFT and then pass the results. I used some kind of a low resolution in a way FFT, but it was kind of, I tried different parameters. And then I passed it to a very simple neural network for learning. And then I used, as I said, IVES. IVES is a tiny machine learning framework that was developed by Fraunhofer IMS, which it's a research institute that works normally on microelectronics. So this is designed to even fit inside a sensor chip. And the idea is almost anything that can run GCC can run this thing. So you can even run it on an 8-bit Arduino with 2K of RAM, but it flies on the Portenta because also take advantage of some of the accelerations that are in the Cortex-M processors. And the neural networks can be trained directly on the device. It's got a lot of more features that I can explain. You should go to ives.ai. But one of the things that's very interesting that's happening right now is that they are working on this IF Express, where you can basically specify a neural network just by one line of code. You pass different numbers separated by comma, and each one of them represent how many neurons you want in each layer, and it will build for you a neural network. So this is an Arduino Uno reading a trackpad and understanding digits in 8-bit 2K of RAM. Imagine on a Portenta. Then I went to the Arduino Cloud and I built this thing, which is basically an interface that you can use from a browser or from a phone, where I can start all the different phases. So all of the code is that I need to build all of this is basically generated once I specify the kind of parameters, the kind of properties I want to exchange with the device. The system generates the code for the microcontrollers, generates all the information needed to build this dashboard. So I just drag and drop the widgets on a page, and then I can pick them up with my mobile phone if I want to. There's an app on the App Store for that. And then basically I get this program for my Arduino Portenta with all these areas where I just fill in with the different bits of code. So I can calibrate, I can train, I can select which pattern to train. Then I can hit run, and then I get this output indicator that tells me if we are in one of the prescribed patterns or we are deviating. And then I also use the NodeRed. This is a hosted version of NodeRed, and we have an official NodeRed interface. So the sort of teal box that you see on the screen connects to the Arduino Cloud and extracts the output property of that device. And then I can use it to build other graphs, build other interfaces, and I can also send it to services like if this and that to generate notification and different things. So how did it go? It was a bit of a journey because I had to try different techniques, experiment with different ways to process the data. The neural network is very rudimentary because I'm not an expert in any way. It's actually derived from a code that would do gesture recognition, so it's a bit strange. It's not perfect, but it's working in a way, so it gives me a direction that we could do this. And so we are going to be testing it with the industrial customer, going to be iterating a little bit on this thing. But it's interesting because a lot of the building blocks that I needed were already done and prepared. So I could just take the FFT library, put it in, and it's done. So and in this setup, I even have a Cortex-M4 to spare. Actually, I could probably run this whole thing on the Cortex-M4, and I would have a Cortex-M7 ready to do something else. So in the future, we'll release the code for this as a tutorial, but at the moment, still tweaking. But it's a promising start. Let's look at that last example quickly. This is, I call it tiny computer vision, because again, as I said, we are surrounded by mechanical indicator. Especially a lot of equipment have these mechanical indicators that indicate the number of hours they have operated or certain events or even power consumption. And you can see some, public counters, meters of different kind. So I wanted to build a simple device that could be basically plugged on top of one of these things without changing, without modifying the equipment. And then I wanted to train it to understand, to recognize the digits and bring the data to the cloud. So I use this Portenta Vision Shield with the LoRa module on it. Then I created a equipment simulator. It's a box that contains this device, which has an hour counter and a sort of pulse counter. And I put another Arduino 33 IoT inside that if I want, I can control from the cloud. But in this particular case, it's just generating pulses with kind of a random delays. So it simulates these numbers changing. And then you can see already that this is going to be very fun to work with because of all the reflection, because this has some kind of a lens to make the digit bigger, but it picks up reflections from a lot of different directions. So I decided to build this box out of opalescent white plexiglass, which diffuses the light and creates this thing that I can actually just snap on top of this meter. And then I have my Portenta mounted at the back. It's a bit crude, but it works. So you can see it here in place. So it's now it's time for me to develop the actual code. So I used OpenMV. In OpenMV, you get a preview of what the camera is looking at. So I started to look at the image, extract the image, and then I tried to understand what kind of filters could I apply to the image. So for example, in this case, I'm using a threshold. I was interested in the number below, so I didn't try to figure out an algorithm that would work for the whole image. So now that I have the ability to extract this image in quite good black and white, then I built an application using the processing language, simply because I'm very familiar with processing and I can code very quickly. So this allows me to put this little green rectangle around the digits, and then it generates a list of or region of interest that I can pass to the Python code in order to understand the different digits when the system is running. And then I started to extract different images of the digits. So you can see some of them are black and white. Some others are in gray levels. So obviously, the more images you capture, the more reliable it becomes. So here I used a very cool feature of OpenMV that allows you to collect data sets directly from the camera in every sort of in a way label. Every category has a little folder, so I can put different images in the folders. So what happened there, I used the region of interests I gathered from my processing app in order to isolate the different digits. And then there's a super cool feature, because if you need to do training, you can use something like Edge Impulse, as we see in a second. But directly from OpenMV, you can press a button and push this data set directly to Edge Impulse. So you can see here my data set landed inside my project on Edge Impulse. And then I started the process of building what they call an impulse. So in this case, I'm taking the image, I selected a certain image size to, depending on the kind, so there was a compromise between precision and speed. And then I'm using this transfer learning for images. and then it identifies that I have essentially 10 labels. So I press a button and I go into this other stage where the systems try to figure out what are the features. So if we go here, after this process, the system has identified different features it will use to recognize the images later. And then I went through the training process. Note, this picture is from the very first try I did. I only had one image per class. So clearly the result is horrible. So obviously I took a ton of different images later on to improve the model. This was just the first try. And then once you have trained the whole thing, you basically end up with a nice trained model that can then recognize digits. So you have different options when you go to the deploy button. You can see up there is an Arduino logo. So if you hit on that logo, you get a ready to go Arduino library that you can use in the Arduino C++ sort of compiler development environment. And you can also use it since Arduino is sitting on top of EmbedOS on a lot of these platforms like Portenta, then you can also use it in EmbedOS through Arduino. Or you can download it as an OpenMV, basically a piece of Python code with a trained TensorFlow Lite micro model. So that's what I did. So I went here and I started to try to understand if the system was able to detect the different digits. I had to fiddle quite a bit in order to figure out a way to extract a portion of the image so that the recognition would happen only on that particular piece of the image. But then you can see that after a few tries, the system was able to recognize the individual letters and individual numbers and then produce the final digit. Then in this case, I could use different ways to send the data. So for example, in OpenMV it's very easy to use MQTT or just HTTP, or it even supports our LoRa, the LoRa part of the Vision Shield. So we could take this data and we could send it, for example, to a cloud through LoRa. It's an interesting protocol because if you're working, for example, in a remote location, you can, it's very useful, but it's also quite robust enough to be operating in an industrial sort of setting. So there's quite a lot of experimentation that can be done and quite a lot of work that can be done around this thing. The data set at the moment is quite primitive. One of the things I would really want to do is to capture really a lot of images from a lot of different fonts that are used in this kind of devices to build a much bigger, much more sophisticated model that will allow me to build something that I can just snap on top something and I don't have to train it specifically for that particular device. But it was interesting because in the end, using the Portenta OpenMV Edge Impulse, it's not a huge amount of work to do this. It doesn't require like a deep understanding of computer vision and machine learning. The results, in my opinion, are encouraging. This device could be really useful. Again, the Arduino ecosystem provides all these different partners, services, tools, libraries that kind of help you every step of the way. Because one of the big things that we are seeing right now is that a lot of these people who are adopting Arduino in an industrial setting have the issue that they are struggling to find people that know how to build these kind of things. And effectively, right now, there's a few million people in the world who know how to use Arduino. So they can just open the door and grab somebody and bring it in, and they would find, while especially smaller companies have a hard time finding people that can help them. So again, when the code is refined, we'll probably release the example. So, well, this is it. This is what I wanted to show you. It is possible to build this kind of devices. as soon as I started working on this, then I had like a million other ideas, but the presentation is 25 minutes long. So thank you very much for your attention. And if you have any questions, I'm here. There's a live Q&A session starting now to continue the conversation. To take part, join us on Zoom by clicking the yellow button just below the video player on this session page.